Like we have about another minute or so. We'll let some people join. And for those of you who have joined, feel free to take advantage of the chat. If you have anything, questions throughout the presentation, feel free to send us a message. But all right, well, it looks like we're right at 2 Eastern, 1 Central. So I want to thank everybody for taking the time to join us for our webinar today. We're really excited that we have our partners INTAMSYS with us. So we're going to review some high performance materials, and I'll shortly introduce you to both John Drews and Grant Lutnan. So I'm very excited. Thanks again for joining us. And I think Grant is controlling. Yep. All right. So we do have an agenda today. This is what we want to go over. I think we have about 45 minutes together. So I just want to review a little bit about NeoMetrix. Then we'll introduce INTAMSYS, and we'd like to go over their unique material portfolio. Something that's really neat about INTAMSYS is some of their high performance thermoplastics. So we'll go over those materials and their applications. We'll be able to review the INTAMSYS printer lineup, and we have some neat case studies that we want to share with you at the end. So this is what we have that we're planning to go through today. And here are some very popular industries that you're going to find 3D printing in. And a lot of these industries have been utilizing 3D printing more and more every day. So they're in every industry from aerospace, marine, medical, art and sculpture. And, you know, the list goes on. For those of you who are joining us, it'd be great if you could just let us know, which industry are you in, and, what type of 3D printing applications are you currently doing, or are you interested in doing? All right. And then, so a reminder about NeoMetrix. We were founded in 2003. We're located in Lake Mary, Florida. We have 3D experience using 3D scanners and 3D printing. We offer services for 3D scanning. We generate CAD files for somebody who maybe has a part. They don't have the CAD files, so we can do a reverse engineering project for that. And also for scanning, if they have a part and they want to make sure that they're manufacturing it correctly, you might want to compare it back to the original CAD. So we can do a scanning service to give a report to see how well that part was made. 3D printing, we have quite a few printers here. Sometimes customers like to send us parts to print out. We also offer 3D printing equipment. So oftentimes customers find that they want to be able to print out the parts themselves, take advantage of having printers using them all weekend during holidays. So it's just neat being able to pair customers with the right printers. We also offer software training for all of the equipment. And you see on the right, we have quite a few different partners. And today we're working with INTAMSYS. So I'm excited to introduce you to that team. All right, and I think John was going to start first. So I'll let John step in now.
Thanks so much, Kelsey. Appreciate that. So again, yeah, thanks everyone for joining. I'm John Drews, and my role is as channel sales manager is to support NeoMetrix and our partners, and not only their sales efforts, but also in supporting our customers. They're your first line of support, but we're right behind them and work with them every step of the way. So that's me. Grant Lutnan is going to be our primary presenter. Maybe Grant, just a couple words on you, and then I'll just do a quick fly through on who we are, and then get to the meat and potatoes. So.
Yeah. Thanks, John. So I'm Grant Lutnan. I'm the technical engineer for the Americas. So I'm in charge of doing a bunch of the support, designing how that all go is working with applications, new benchmarks, kind of like the lead technical guy for INTAMSYS. So I'm really looking forward to walking you through some of our materials today. Thanks, John, for the introduction. I'll toss it back over to you to give a little bit about our history.
Sure, thanks. Yeah. Like I said, I'll kind of keep this brief. Some of you may know of us, others may not. So just to kind of bring you up to date, the picture that you see here, that's our corporate headquarters. We're based in Shanghai, and that's where all of our R&D production is done. But in case you're not aware, INTAMSYS, the name does have a meaning. It kind of comes from the 4 words that show there on the top of the slide: intelligent additive manufacturing systems. So that's what we're all about. Again, established in 2013, talked about our headquarters, our US headquarters. We have had established now about a year, but Minneapolis, Minnesota, we're the newest, I call it division or group within INTAMSYS. And then we got a European headquarters in Stuttgart, Germany. So significant investors in us, Porsche, Sequoia, others. But I guess the good news, we got over 3,000 systems installed. And I still believe we're the #1 global printer for PAEK, and a lot of other products too, but just a little on that. All right, next, please. So just to kind of go through, and I'm not going to talk about that, but just knowing we first were, incorporated, we came out with the FunMat HT. We've continued to improve and iterate on that. Along the way, we've introduced new machines. We've had investors along the way. We got a great announcement that just came out this week about our 310. So we're not standing still. We're continuing to innovate. We got investors again that are believing in us and our technology. So we find, like I say, a lot of exciting things ahead. Next slide, please. So I guess a little bit on what we're all about. Again, our cornerstones, we call them, but intelligent systems. I won't go through all of these details. We'll hit them, I guess, when we go through some of the product slides, but really focusing on being easy to operate. And you'll see as even this new machine come out, the 310, just how we're making it even easier to operate. Best in class material offerings. One thing unique with us, not unique, but I think is, a benefit is we're an open materials platform. So we got a line of INTAMSYS materials. You're not locked in, and obviously the low total cost of ownership is important when you take into account the cost of the machines, materials, maintenance, and ongoing. So next slide, please. Global, again, won't go through all of that. These are just the blue dots here where we have partners. Again, we don't necessarily sell our printers direct. We work with business partners, and we're there right behind them, working to help support their efforts. Again, not only on making sure it's the right printer for you, but also after you do invest in the printer, if there are any questions or things we can assist on. But I guess that's, next slide, please. So we're a complete system, got the software, again, not only for the slicing, but also intelligence built into the machine. The lower screen there is what you might see on the machine interface. Broad portfolio of materials. I mentioned open systems, and obviously you need the printers that can print those engineering plastics and high performance polymers. So next slide. Okay, well, that was longer winded than I thought, but Grant, I'm going to turn it over to you and get down to what the webinar is all about. So thanks much.
Yeah, thanks, John. Yeah, so we're going to get into talking about our material portfolio. We'll start out from kind of a broad overview of our portfolio, and then we'll deep dive on our high performance materials, which is something that we're specializing in. So you'll see here, we have everything from something like a consumer grade material like PLA into industrial or engineering grade materials like ABS, ASA, nylon blends with carbon fiber, a bunch of PC and PC blends. And then today we're really going to focus on talking about PAEK, talking about PEK, PEEK CF, PEEK GF, Ultim, and PPSU. These are what we will call high performance materials. The great things about some of our materials are when you're using our materials with our slicing software and our printers, we have all of that tuning profile done for you to give you a super excellent user experience. We have data sheets that will let you know how strong your part will be, and a bunch of other data based on printed results that we've done on our machines. We take really good care to make sure our material is very, very high quality. So lower quality materials will have a variance in diameter as it goes through the filament. Ours max is plus or minus 0.05 millimeters, which is really great. One other thing that we think is super important for FDM is the ability to be able to dry your material. So we make sure that every spool can go into an oven at the appropriate temperature for extended periods of time to actually dry the material. So if you're printing PAEK, you have it on a different spool that can withstand 150 degrees Celsius. Whereas if you're printing with ABS, that's on a spool that's lower temperature that can do 100 degrees Celsius in the oven. But anyway, your spools will not melt when you dry material. It's a bigger thing than it should be. With that, we have drying specifications for our whole lineup. And then our cost for materials is also very competitive. So on the left here, you'll see our performance materials. Like I said before, that's PEEKs, PECs, Ultim, PPS, PPSU. Our engineering's there in the middle. We do have TPU and then the support materials on the right. So we do have custom support materials for all of our materials. Some of these are water soluble, some of these are semi-soluble, some of them are breakaway, but all of them are specifically designed for the materials that they go with. So they can withstand the chamber temperatures required to print that material. This is really important when we're talking about like Ultim 1010 and a chamber temperature of 225 degrees. You need a support material that's also able to withstand that chamber temperature without deforming. So moving on, we'll kind of get into a deep dive about each material. PEEK is a really important material for us. It has really excellent tensile strength, has really great impact and wear resistance, very high chemical resistance. This is one of the reasons that it's chosen so frequently. PEEK parts, printed PEEK parts, can actually go into a cleaning enclave to be sterilized. For that reason, they can be sterilized to the extent that they can be used in the medical industry. PEEK parts can be used up to 260 degrees Celsius after annealing. So really where we're seeing PEEK used the most is in medical device and manufacturing applications. These parts are frequently coming into contact with like clean room environments where they need to go through a sterilization process. I think one of the absolute coolest applications that we've done so far is we actually 3D printed a gyroid structure in PEEK where a university actually grew bone inside this structure with the intention that they could then implant that PEEK part into a bone and regrow the bone attaching to that PEEK part to kind of like strengthen a damaged piece of bone, which is absolutely incredible. I won't cover the data on the bottom on any of these slides. We have data sheets available on our website, and you can look at them here on the PowerPoint or on our website at your leisure. Additionally, if you have any questions, feel free to put those in the chat. this presentation works best when you're just, any question you have, you toss it out there. We can have a conversation about a more specific application. Moving on to our PAEK CF. So this has all the benefits of regular PAEK, except for it's stronger before annealing. So straight off the printer, this has a very, very high strength part. Most of the time, I'm not annealing my PAEK CF parts. It has an excellent surface finish. So if you have a high temp, but like visual application, you can use PAEK CF and have confidence that you're going to get a beautiful looking part that's also very strong and very temperature resistant too. You can use PAEK CF up to 315 degrees C. For all of these reasons that I've mentioned, it's commonly used to replace aluminum brackets. So if you think of a lot of aluminum CNC machined parts, most of them can actually be 3D printed in PAEK carbon fiber and be like a direct one-to-one replacement as an end-use part, which is pretty incredible. Moving on to PAEK glass fiber.
Hey, Grants?
Yeah.
Yeah, we had a question come in, and you talk about, you know, PAEK carbon fiber, and does that require a special type of nozzle or tip, and, you know, as opposed to regular PAEK? Just, you know, wondering what the options, are there. So.
Yeah, great question. So regular PAEK will use a copper alloy nozzle. And the purpose of this is to reduce the heat cycles required to get the heater up to temperature. One of the biggest challenges of printing PAEK is premature annealing. So if we can keep the heater pumping as few cycles into the heat block as possible to liquefy the material, that helps us avoid premature annealing. When we're printing with PAEK carbon fiber or PAEK glass fiber, we actually switch and we use a nozzle with a copper core, but it still has a hardened steel tip. So that gives us good thermal transfer without the wear at the actual exit of the tip. If you were to print PAEK carbon fiber or PAEK glass fiber with the entirely copper alloy tip, you would quickly no longer have your 0.4 or 0.6 millimeter nozzle. It would be wearing away into like a 0.8 or even a 1 millimeter nozzle, which is not what we want when we're printing high precision parts. I hope that was a good answer for that. Definitely put it in the chat if you have additional clarifying questions.
Yeah, no, thanks, Grant. Appreciate the clarification. So I'll keep you posted if we get more that come in.
Thanks, John. Moving on to our PAEK glass fiber. So we have all the benefits here of regular PAEK. We still have the chemical resistance. We still have super high tensile strength. Again, we're stronger before annealing. PAEK glass fiber is one of those materials that can be annealed again. That I usually end up using straight off the printer without annealing. Again, we have a use temperature up to 315 C. Benefit of PAEK glass fiber is it's non-conductive in comparison to PAEK carbon fiber. But then we get that excellent surface finish it's mostly used again in these manufacturing applications for high strength brackets and aluminum replacement kind of applications. So these are best used when there's a complex geometry that might be expensive or difficult to CNC machine. Odds are, even if it's not difficult to CNC machine, it's still cheaper to print in PAEK carbon fiber than it is to CNC out of aluminum. Moving on to our last semi-crystalline material, PAEK. So PAEK is mechanical properties kind of comparable to PAEK. It's a little bit easier to print than PAEK due to a slower crystallization. So when we heat it up, it's a little bit less likely to fully crystallize while we're printing it. When we're printing these semi-crystalline materials, it's really important that they say semi-crystalline and not go fully crystalline. It has a higher TG than PAEK. You can use it up to about 160 before annealing instead of 143. And then,
Hey, Grant.
Yeah.
I don't mean to interrupt again. I had another question come in, but you've mentioned annealing in several of these materials, and can you maybe just explain a little bit about what annealing does for us, how hard it is to do, and when you might want to do it? I think that, I mean, yeah, it sounds like there's at least some of these materials that could benefit from annealing, but anyway, yeah, so.
Yeah, happy to. So annealing is the process of taking these semi-crystalline or amorphous materials and transitioning them into their final crystalline form. What that means, and the purpose and why you want to do that, is when we anneal these parts, they're getting drastic increases in temperature resistance and use temperature. You'll see we're looking at a glass transition temperature of 160 C for PAEK. But after we anneal it, that goes all the way up to 260 degrees Celsius. So that's a huge benefit from going through the annealing process. Another thing that we get a significant benefit for is tensile strength. And specifically, additionally, tensile strength in Z. So we can actually increase our layer-to-layer adhesion by going through this, this annealing process. The last kind of benefit that you get is significantly increased chemical resistance. So because of the crystalline structure of the material after annealing, you get significantly better chemical resistance properties. This is what's allowing these materials to go into like a cleaning enclave. Now, annealing as a process is basically taking a printed part and baking it for a period of time. And then once that baking is done, you'll have an annealed part. There are some specific key points to kind of watch out for when you're going through the annealing process. When we're heating something up to 150 and then 200 degrees Celsius, especially a thermoplastic, there's an opportunity for that part to deform. For that reason, we really like to plaster cast all of our parts before they go into the annealing oven. And that's just basically mixing up some soupy plaster, dunking your part in, pouring some more soupy plaster over the top, let it set so it's hard, and then take that part encased in plaster and put it in the oven. There's a ramp cycle to go through. So you'll go to 150 C for a few hours, 200 C for a few hours, and then back down to 150 C and then down to 0. It's really, once you get it down, it's quite a straightforward process to go through. It's just, put a part in some plaster and bake it. Once it's out of the oven, the plaster crumbles away pretty easily. And you get amazing benefits from being able to do that annealing process. If you have additional questions about the annealing process, definitely put them in the chat and I'd be happy to answer them.
No, thanks, Grant. Great explanation. And I know we've done a lot lately with that plaster and kind of, like I say, it takes a little bit to kind of tweak it in, but yeah, we can help it there too. So again, thanks much.
Yeah, so moving on to finish out our PAEK. PAEK is again for that chemical resistance application and temperature resistance application. PAEK can go through a cleaning enclave and resist harsh chemicals. So it's frequently used in medical device applications. One of the unique ones that we found is actually for a tool holder for sterilization equipment. So actually a cleaning enclave itself needs to switch tools occasionally, like switch a head for the sprayer, and it can actually go over, drop that head into a holder, a bracket made of PAEK that's able to withstand the temperature that might be at and withstand the chemicals that might be on that while it switches to another one and continues on with its cleaning process. So super, super cool application with a really cool material. Moving on to PEI or ULTIM. ULTIM is a trademark name for PEI. We'll start out by talking about ULTIM 1010. ULTIM 1010 has super, super high tensile strength, super, super high flexural strength. It's a very stiff material. It has good chemical resistance, not in the same ballpark as PEEK or PAEK, but good chemical resistance. One of the reasons that ULTIM 1010 is chosen is for its flame, smoke, and toxicity rating. The flame, basically when ULTIM catches fire, the flames or the smoke that it produces are non-toxic. Additionally, ULTIM 1010 is self-extinguishing. So if it catches fire, not only are the smoke particles non-toxic, but it will put itself out. For this reason, it's mostly used in aerospace applications. So there's ULTIM 1010 parts on a lot of airplanes, a lot of spacecraft are using 3D printed ULTIM 1010 parts today. That's for interior parts, but also for functional parts. You can use ULTIM 1010 up to 200 degrees Celsius. It's very high tensile strength. You can use it in mechanical applications as well. Oh, yeah, there's ULTIM 985. So ULTIM 985 is kind of the sister to ULTIM 1010. ULTIM 985 has, again, good chemical resistance, good low flame, smoke, and toxicity rating. It can be used to 160 C. Kind of the difference between ULTIM 985 and ULTIM 1010 is ULTIM 1010 is very stiff, very high tensile strength. ULTIM 985 is still high tensile strength, but it's flexible. For this reason, ULTIM 985 ends up mostly used in like aircraft ductwork. Again, you have the flame, smoke, and toxicity rating. So if you're pumping heat into your airplane, you don't have to worry about any of your ducts like catching fire or having any issues there. Use temperature up to 160 C. And then it's flexible. So as ductwork is vibrating, as air is passing through it, it's very resistant to being able to like take some of that vibration and still maintain its shape over long term. Additionally, ULTIM 985 is frequently used for aircraft interiors. So think armrests, think bezels for windows, that kind of thing. Moving on to some of our more niche high performance materials, we have PPSU. The super unique thing about PPSU is it has high hydrolysis resistance, which means it doesn't degrade when submerged. All of the previous high performance materials we talked about, even the PEEK and the PAEK, if they're submerged in chemicals or liquid for an extended period of time, they will start to degrade. That's not the case for PPSU. PPSU also has really, really good chemical resistance, up there with PEEK and PAEK. Additionally, resistant against gamma rays, can be used up to 180 degrees Celsius. For all of these reasons, we mostly see PPSU used in applications where it's submerged in chemicals. One of the applications that we've seen PPSU used for is on-demand parts for embalming equipment. So pretty weird application, but if you think about it, embalming fluid is basically a cocktail of chemicals that needs to be pumped through a human body. Those pumps have mechanical parts that fail. They're not resistant to supply chain issues. So being able to 3D print PPSU parts for embalming equipment is a huge value for this application. This is our last material here that we'll talk about today. This is our VICTREX PAEK AM200. This material is super cool, almost basically one of a kind for the 3D printing industry. It's very, very similar to PEEK. It's intended to be used as a PEEK replacement. So you can do all the cleaning enclave stuff, all the sterilization, high use temperature, all of that, still exactly the same true for PAEK. Has slower crystallization, so it's more like PEEK. Slower crystallization means easier to print. It's one of the coolest defining features about PAEK is it's nearly isotropic. That means it has nearly the same tensile strength in Z as it does in X and Y. Really, when we're looking at 3D printed parts, even high performance 3D printed parts that have been annealed, we're chasing like 40% maybe of the strength in Z as we are in X and Y. And that's just the reality for FDM 3D printed parts up until this point. You'll see below, we actually are able to achieve more like 70 to 80% of the tensile strength in Z as we are in X and Y, which is nearly unheard of in the FDM thermoplastic industry. So this is a super cool material if you have a PEEK application that requires, a uniquely shaped bracket like this, where it's getting stresses in a bunch of different locations, needs high chemical resistance, super, super high performance material, but absolutely worth it for the right application. So when I'm talking about all these materials, I'm talking about, we have, this very high tensile strength. And I want to give you kind of like a scope of exactly what tensile strength we're able to achieve. So on the right is kind of like a standard aluminum alloy. And we'll see, just a little bit over 100 megapascals of tensile strength. What we're able to achieve with 3D printed parts is like for PEEK and PEEK, 98 megapascals. That's right up there with aluminum. So a lot of times we're able to get, 90%, 80% of the tensile strength of aluminum on a 3D printed part without the need to go through a CNC process that's expensive, has long lead times, very wasteful for raw materials. We can normally 3D print a whole bunch of materials that'll directly replace aluminum in a lot of applications, especially when you consider the use temperature of a lot of these materials as well. So now we'll move on into talking a little bit about the 3D printers that we offer and which materials kind of go on what systems and why. So we'll start out with our FunMat HT. This is a 450 degrees Celsius extruder, 90C chamber, 160C build plate. It has automatic bed leveling and a ceramic glass build plate. This little printer is actually capable of doing almost all of our materials. The only ones that we have to leave out are Ultim 9085, Ultim 1010, and PPSU. The reason for that being is just the chamber temperature does not quite get hot enough. All of the other high temp materials that we talked about today are able to run on the FunMat HT. So PEEK CF, PEEK, PEEK, PAEK are all able to run on the FunMat HT. Really, really incredible way to kind of dip your toe into high performance materials.
Something else just wanted to add to the HT is the size. It has a build plate of 10.2 inches cubed, so it's really a large desktop printer. So that's something that we really enjoyed using here is the size of the desktop.
Great addition. I do not know how that missed my slide. Moving on to our FunMat Pro 410. This is our mid-tier machine. This has dual extruders, so you get a model material and the support materials that I was talking about in the beginning. This has the same 90C chamber, the same 160C build plate, also has automatic bed leveling with the ceramic glass build plate. One of the key points that the 410 has that the HT does not have is that 410 has a temperature controlled filament cabinet. And why this is important is a lot of these high performance materials are very hygroscopic. What hygroscopic means is just that materials want to draw in moisture from the air around them. When you have a heated filament drawer, you're controlling that process. So you're trying to limit the amount of moisture that materials are absorbing over time. This is really important when we're printing PEEK. This is really important when we're printing PAEK, PEEK CF, stuff like that are very hygroscopic. If you're not printing them with some sort of moisture solution, you're going to have a pretty big challenge. Additionally, on the 410 has liquid cooling. So when we're printing things like PEEK, where it's really important to have the material as cool as possible, then get liquefied and then cool down again very quickly. We have a liquid cooling block directly above the heater that keeps material cool until the last possible second, where it gets liquefied and then cooled down quickly so that it doesn't prematurely anneal. And the build volume on the Pro 410 is 12 inches by 12 inches by 16 inches in Z. And then moving on to our top of the line system is our FunMat Pro 610. This has dual 500°C extruders. It has a 300°C chamber. So this is where we get to print Ultim 1010, Ultim 985, and PPSU. So because we have a 300°C chamber, we're able to print these really, really high temperature, high performance materials in a large format as well. So the Pro 610 is a 20 by 20 by 24 build volume, 24 in Z. It has additionally automatic leveling. You'll print on a PC sheet or a sprayed steel sheet, depending on what material you're printing. For the high temperature sheet, or for the high temperature materials, obviously you can't print on a polycarbonate sheet. So we have a sprayed steel sheet that you print on, and that gets sucked down to the build plate with a vacuum system. So we have an onboard vacuum pump that's making sure these sheets stay flat and in the exact spot that they need to on the build plate, and that they're not moving left or right at all. One of the best things about the Pro 610 is we'll do an automatic material changeover. So once one spool is empty, it'll recognize that, automatically unload that material, and then load new material in afterwards. When we're talking about the moisture problem that we're talking about with the 410, with the heated filament cabinet, this additionally has a heated filament cabinet, but even we're taking this one step further, and we actually pump dried air. Basically, there's a dryer on the system, air comes through, all that air gets supplied to each of the filament cabinets, additionally with heat. So between that heat and that dry air, you can print these really, really large high performance material parts that might take a day or 2 days or 3 days, where you're really up against this material potentially absorbing some moisture over the duration of the print even. We're able to manage that. And then last but not least, we have the same liquid cooling system strategy for the 610. The liquid gets pumped up to a cooling block at the head. Material stays nice and cool until the last possible second where it gets liquefied, and then cooled very nicely again afterwards. And this is really allowing us to set ourselves apart when specifically printing PEEK. There are some competitors that also print PEEK. There's not very many, and there's not very many that are also doing it as well as we are. That's because of our high-powered cooling fans. That's because of our liquid cooling system. I truly believe that we have it as dialed as anyone in the industry. And then I'm going to hand this back off over to Kelsey to go through a couple of the applications and kind of case studies that Neometrics has done with the
Sure.
INTAMSYS machines.
Yeah, thank you very much. That was really helpful that you went through all the materials and the advantages, and thanks for going over an overview of all the printers. We have actually these two printers that you see on the screen at our facility. We have the FunMat HT, the FunMat 410 Pro, and we've been really enjoying using both of them. There's a couple of unique applications I wanted to tell you guys about. If you want to switch to the next slide. The first one was a really neat application we had with Nexar Avionics. They upgrade instrument panels for existing aircraft because they want to incorporate the latest digital instrumentation. Excuse me, I'm a little bit sick, so bear with me. But in the process of upgrading, they found that they had a glove box that they needed to replace. This glove box was actually not able to be found from the manufacturer. So the only solution they had was to make it themselves. So they gave us the original. It was a reverse engineering project. So we used one of our scanners. We captured a point cloud. Then we were able to generate a CAD file. The neat thing we were able to do is actually generate one file, whereas the original piece was actually multiple components. So it was an assembly. But then since we have it down to one file, we're actually able to use the STL file, send it to a printer, and it was now able to be printed in one part. We actually did this with ABS. It was a great material, and we printed this on the FunMat HT. It was such a great application. They ended up getting their own HT, I think, to continue making these, and I imagine many more parts. Another example in the bottom is, this was a customer, is a worldwide manufacturer of laboratory equipment. And so you'll have containers, being worldwide that have to be connected, and they might have threads that could be in metric or in English. So sometimes you'll need an adapter to fit them together. So they had an adapter, but with today's supply chain issues, those adapters were difficult to come by. So it'd be a lot easier if they could make them themselves. So again, this was another reverse engineering project. We were able to scan the outside of the adapter, but the challenge was in this particular application was to get the inside, because the scan is just difficult to get inside. So we ended up using a technique we created a silicone casting, so we were able to capture the threads on the inside. So once we had that information, we were able to actually finish the completed CAD file. So we had the inside information, the inside geometry, as well as the outside. We had a completed CAD file. And in this application, being that it was a food industry, PAEK ended up being the selected material. So we used PAEK, and we ended up printing this in our 410. But it turned out to be a great part, another great application. So these are just a couple things I wanted to share with you guys today. All right, well, I guess that concludes our presentation. Thank you all for attending, and I especially want to thank INTAMSYS for joining us. You have all of our contact information. So as always, feel free to reach out to any of us. You can reach out to me at Neometrics if you have any projects in mind. Perhaps you have a reverse engineering project. Feel free to send me an email. We can talk about it. If you need any parts printed, we're happy to help you with that. Or if you're really dying to get your own printer or even scanning equipment, just feel free to reach out. But we'd love to help you. And I guess if you guys want to say any closing things.
No, thanks, Kelsey. Good wrap up. Appreciate everyone joining. Like I said, we get some great, printers, and Neometrics is a great partner. So again, thanks everyone, and I hope to be talking again soon. Take care.
Yep. Thanks. Bye, everyone.
Thanks.